Howdy, folks. All right, today we're going to talk about covariance and correlation. And what are those things? How do you work with them? What do they mean? All right, let's get to it. So we've taken a look at variance, and we now understand how error is associated with understanding data sets, right? Covariance is the concept that given two variables, sometimes they trend together. So in other words, sometimes they have some directionality to them. When x increases, y decreases, for instance, if its covariance is less than 0. Other times, and probably what you think of more commonly, in other words, maybe something like size and weight of well, almost anything. We tend to think that as size increases, weight generally increases as well. That can be a positive covariance, and so when x increases, y increases, or neither. As covariance approaches 0, it's quite simply that y doesn't care what x does. X can increase and y can go in just about any direction it wants to. The important thing here is this is a description. It describes the relationship between these two variables, and is really useful for understanding a data set that you've collected. So it's a great descriptor, and it's one you're going to see a lot. The best way to think about it is that when x increases, so when you have your independent variable and you're taking and you put it and you line it out across the x-axis, and you say when it increases, what does y do? What does the y component of that do in the data set? So positive covariance is when y tends to increase when x tends to increase. In other words, size and weight. Negative or below 0, numbers below 0, are negative covariance is when x increases, y tends to decrease. And these can be vice versa, right? So as y increases, x decreases, or as y decreases, x increases. You can line them up many different ways. It's just that saying that they are have positive covariance and negative covariance tells you that those variables have some type of relationship with each other. That when one does something, the other is in some way predictable, or tends to be predictable. So this is important because as your covariance approaches 0, you lose that aspect of it. It's not that the two don't have markers associated with each other. It's just that when x increases in an uncorrelated set of variables, as x increases, y just doesn't care. It can go up, it can go down. It just doesn't care much about x, and you can see that in the middle of this picture over here. So that as you go from left to right on the x-axis, y does not trend in any particular direction. So you can calculate covariance, but we are not going to, because we're going to go right to correlation, because correlation gives you the directionality of your covariance in addition to a marker of strength. So some indication of how well those two things trend together. So it's excellent for describing this type of relationship. It gives you both. So we're going to go, covariance is a part of correlation, and we're going to be calculating correlation here in a second. But I wanted to pause for a second to really emphasize this point. We're now really getting into how to describe data. And you're going to see this frequently, and you do see it frequently, but hopefully now you start recognizing that this is where that error of correlation does not imply causation comes in. I thought this was a pretty clever approach on the right, where confusedwords.org does a good job of describing the difference between the two. From our data sets, we want to make inferences. We want to infer things that are arguable. In other words, things that we can well defend based on data. That's an inference. From whatever example you want to draw, if the thing you're saying, the statement you're making, is based on those data, then you're inferring a relationship. The point at which you imply something is when you leave it, I guess you might best say unsaid. But it's not implied that there's a causal relationship between the two. If you can infer that relationship by providing additional supporting evidence, then you are doing a good job with your data. If you just point at a scatter plot, and if you just point at a correlation in R, and a result of an R calculation, then you are implying, and you are not doing a good job of making an argument. Just pointing at scatter plots and pointing at statistics is making an implication. Using those figures to further explain how and why the two variables might be connected or behaving in that way is making an inference. So there are many different examples of this out there where you can imply two variables are correlated when they have nothing to do with each other. And there's some very hilarious examples of that out there. But I'll leave that to you to discover. It's a pretty common, I don't know if mistake, but it's a way that folks try to use their data in ways that aren't appropriate or aren't correct. So always look for making inferences, not implications. Okay, so with regard to correlation, we're going to calculate correlation coefficients, or Pearson's R. We designate this with rho, or just R for us. And it measures both the closeness and direction of movement between two variables. It will range between 1 and -1. Anything from 0 to 1 is what we call a positive correlation. So the covariance we just looked at is from 0 to 1. That means as x increases, y increases. Anything from 0 to -1 is negatively correlated. So that is as x increases, y decreases. And you can shape those differently. It's just that this is the most common piece. But what's nice about the coefficient, correlation coefficient, as compared to just covariance, is that it provides us an indicator of strength, or the indicator of the how predictive this data set is of y given, or x given y. So when we look at up here on this top run here, a correlation coefficient of 1 means every single point falls on a line. So that x, anytime you figure out x, it's a perfect predictor of y, of where the y component will fall for two different variables. The positive one just means it's moving, x increases as y increases. A correlation coefficient of, or R, of -1 is equally strong. It's just that the data points move in the opposite direction, which is to say as x increases, y decreases. But equally so, for every time you know x, it's a perfect predictor of y. Now, in reality, in real data, I've not seen where you actually end up with perfect predictors like this. There's always some amount of variation in any type of actual, especially archaeological data set. This just doesn't exist. It always falls somewhere between 1 and -1. And that's where a lot of the work begins, or a lot of what you need to know as you approach reading or understanding data begins. So we know that 1 is a perfectly straight line. Every point of y, or every point falls on the xy axis exactly where you can predict it. And the same is true of -1. 0, as we talked about in covariance, remains true, which is to say that x is in no way a predictor of y. As you increase in x, y can go willy-nilly wherever it would like. It's in no way is x a predictor of y. That's what 0 means. So similarly, it's not often you get correlation coefficients of 0 with real archaeological data, because you're often setting up your studies of interest, or your spreadsheets, or your scatter plots, with in mind two variables that you think probably are related in some way. But but that doesn't mean you're right. It's just that oftentimes you're going to fall somewhere between 0 and 1, or slightly to the side of 0 and -1. And it's in there that we begin to see these trends, okay? But as you think about this, this is showing you very nicely, I think, that as you move from 1 to 0.8, the error along that line becomes greater. In other words, knowing X is a pretty good predictor of Y, but not perfectly accurate. As you go from there to 0.4 in this case, knowing X is kind of an okay predictor of Y, but it's not great. And the closer that gets to 0 from either direction, the less and less reliable knowing X is as a predictor of Y. Okay. So as you look down here, these are all perfect correlation coefficients of 1. They just have different slopes on their line. As you go 1, 1, 1, you can see that it doesn't have to be a 45-degree angle. The slope of the line can change. It's just that for every X, Y is exactly known. And the same is true for negative correlations. What's interesting is down here, I think, these all have a correlation coefficient of 0. And you can see that knowing X has little to do with predicting where Y might be. In fact, on these, I think we need to do some cluster analysis over here. But on these uncorrelated, where there's no covariance at all, X and Y just exist in the same universe but barely acknowledge each other. However you want to think about that. Knowing X does not tell you much, if anything at all, and in fact, nothing about Y or where Y might fall. Okay, so that's the long and short of that. Let's get back to let's get back to our sort of our discussion of bowling balls and basketballs. For whatever reason, we have these items going, so we're gonna run with it. We took a look at bowling balls. We know the uniform size of 8.5-inch diameter. And we also know about bowling balls that they have to run through a ball return. So they're going to be held to a pretty tight standard. But weight-wise, that's where you see the difference in bowling balls. So 8, 10, 12, 14, and 16 pounds. We ordered up 5 of those in our last example from last week. And we also ordered up 5 basketballs. And we found size classes associated with roughly different age groups. And we ordered up a basketball from each of these 5 size categories, so size 7 to size 3. And here you can see what the official stat, the official size category for these basketballs are. Okay, so we ordered these up, and we want to try to understand how things are related between the two, or how much error there might be between the two. So we're going to do this, and we are going to have some data. So we have our, in this case, basketballs, as you can see here. Again, a big portion of this is getting familiar with Excel and working through things with Excel. So we're going to calculate the correlation coefficient for the data we've recorded about basketballs, and down here is one of the most useful things in Excel that you may or may not be aware of, but if you're not, this is something to get used to. We have basketballs in one tab, and we have our bowling balls in another. So what we've done is taken them out of the boxes that we talked about last week, and we've given each a number. So as we pull that out of a box, ball number 1, measure the circumference, weigh it, and then also record which size category that ball is supposed to be. So we are now able to take a look at some data associated with these basketballs. We've measured the circumference of each, and we've measured the weight of each. And we keep in mind that these aren't just completely unrelated things. We have here a chart of what they're supposed to be. So we know what they should be, but we can get back to that later. Let's see what the sample of basketballs we have looks like. Well, one of the fastest ways to do that in Excel, you just highlight an area of interest. Here I'm going to keep in the label categories across the top. I'm going to go up and insert a chart. Now, oftentimes, this can look very different, right? So just in charts, you can insert almost anything, but first highlight your area. I know that I want a scatter plot, and I want it to be that. So I look at a scatter plot of my data, XY scatter plot, and I can see that they just by visually, in this one, they seem to very strongly have positive correlation. And there does not seem to be a lot of error, but they're also not perfectly on a straight line. Something that can help, if you highlight your axis down here, you can see that I don't need most of this x-axis. I can safely, since I don't have any data in there, come in and right-click there, format the axis. I'm quite simply going to change the minimum on this axis to 20, and that should just give me a little better visual range on that. So let's say I had 4,000 data points on my little scatter plot here. And I noticed that basically everything from 20 to 0 was not represented. By changing the scale on your x-axis, it just gives you a better visual on that. We haven't changed any of the actual data. We haven't changed any of the actual numbers. But what we can do is visually see or represent here a little better the error associated with these. So before it looked like they were on a pretty darn straight line. Now we can see that there is some variance here. But how much or what can we do to describe it? What can we say about these data? And that's really where we want to get some type of correlation. So I just delete that. That's wonderful. The scatter plot looks like we have a relationship there. But now let's find out how we calculate it, or what that actually looks like. So this is the formula for calculating Pearson's correlation coefficient. If you are not accustomed to working through this type of things, or heavily involved as a stats person, it's fine. This is all actually pretty straightforward, and we're going to use Excel to help us out here, because all we need to do is work through piece by piece remember from the inside out on a formula. The thing to keep in mind here, my goal for you folks with regard to quantitative methods, I want you to know and understand the stat. I want you to know and understand what a correlation coefficient is telling you, especially when you read it in a journal article. I want you to understand why it's important that something has a high or a low, in this case, correlation coefficient. But that's true of p-values and on down the line, which we'll get to. So here, as we work through this in Excel, I want you to be able to do this, because also you're going to collect some data at some point. Well, you're going to do it for this class, but at some point you're going to have some data, and you're going to want to understand how two things are related. This is easy to do and very informational if you've just been kind of shown it. So don't look at this as being daunting so much as it's just a procedure to work through, and it will tell you a lot about these things. So let's work through it. We have some columns here, and we have some data. Let's make it a little easier on ourselves to start with. You can do this if it helps. This is just a thing. The way we've labeled things, let's call that the circumference of the ball, our x-axis, and that's our y. Now all that's going to do is, if you need a helping hand, this will help you keep your x values associated correctly and your y values associated correctly as you work through a formula. There is no problem at all with helping yourself out as you work through your data. If you need to and you don't want to work with the raw data set, make a copy and go play around in a copy of your data where you can change it, or I should say put things in, make mistakes, delete it, come back. You've not actually, you should always have backups of your data for sure. But if you're worried about messing something up, make a copy of the Excel file and work out of the copy. You can always come back to your raw data if something goes awry. But in this case, all we need to do is work through the formula. So as we take a look at this, is hopefully helps you out a little bit. I hope it's not like too much of a wall of text, even though it certainly looks like it. We need to work from the inside out. Let's start with the numerator, of course, the top portion of this. So we need to calculate all of the x variables minus the average. average, let's say average of X. We know we need to calculate all of those, and we need to calculate all the Y integers and minus the average of Y. So in order to do that, we're going to need the average X and the average Y. Easy enough. In Excel, you can come up here, and sometimes this shortcut exists for things you're trying to do. Oftentimes it doesn't. That's why you need to know how to use the function thing. We'll use plenty of that. But in this case, to get the average, I just select the down arrow, choose average. It's going to give me this box, which of course I can change. I can pull that around, or I can change the cells in here. I can click on different things. But that is exactly the average I want to know. Similarly, here I could go up and do it again, or I can just go here and Control C, Control V, and get that. Or I can go here and I can get my little crosshairs deal, and I can copy it over that way. That'll move that formula over down the line. Personally, I use Control C, Control V constantly, just because my hands are up on the keyboard and I'm typing things anyway. But as you work with Excel and spreadsheets, you will find things that are comfortable or familiar to you, and have your own pathways for getting there that you prefer. You will also run into people who constantly tell you that their way is better. It's fine. Just nod and try it out. And if it doesn't work for you, go back to the thing that you know and like and use. There's no firm way to do this, but there is a firm way to do this. So we want to calculate our first portion of our equation. So we know we need a formula. So we put in an equal sign. We need X minus average of X. And there's our first result. Now, if I hit Control C, highlight all of these, and then hit Control V, it will be problematic because it's going to run this cell right down the line in association with these. So that's something you have to be aware of. I think I actually made that error and had to go back and fix it back on the variance one. The way to fix it is in your formula here. You can lock a column and row figure by using the $sign. So I want X minus the average of X for all of these, but I want this to stay the same as I copy and paste it across. So we can see that that result's the same, but we've now locked the second cell with $C, $7. Now I'm going to Control C and Control V, and I get accurate figures there. And we can see that that C7 has been locked for each of those. Okay, so there is my X minus the average of X. Let's do Y. We have a function that we're going to do. So we have an equal sign. We have a location of Y minus the average of Y. Okay, looks good. Let's lock in D7 with some $signs. Great. Control C, Control V. Or you can grab it and pull it down. Same thing. Okay. So however you would like to get there works. For me, again, that's how I like to do it. So we have figured out the first portion of solving this. All right. So we then need to, so we have X minus the average of X, and we have all the Y's minus the average of Y. Good. We need to multiply each. So we need to multiply X, let's say times Y. I think most of the time I would prefer just saying XY. Works good for a column. But now we can multiply X minus the average of X times Y minus the average of Y for each instance of XY throughout the data set. So Easy enough. We have x times y in a certain way. There we go. Highlight. And this time I do want it to shift all the way along. So there we go. We have now figured out x minus the average of x times y minus the average of y. Easy enough. Then we have to sum that column. Sum. So again, let me escape here. I just choose this cell. And if I go up here to eta and select it, it's going to sum the range of numbers that I choose. And it looks like that is the sum. Now there's a couple things you can do here as we're starting to get out to the side and some numbers. So don't forget a few things. I could write in here sum. So the same way I've been labeling across the top, which each column represents, I could label there sum, and that might be handy. Another thing that might be handy is since these seem to be sums or averages, or at least in some way different, it might help me out to just put a border there, if that helps you out. Some folks like to put a border here. Oops. Control Z, that undoes it. Control Z to undo. We want to put a border here to represent the end of our data. That's fine. That works out just fine. I'm going to bring this over a little bit for you, cover that up a bit. All right. So there we go. We have figured out the numerator. This is the top portion of our equation right there. Now we just need to solve for the bottom, which is not too bad. We've already calculated x minus the average of x, and we've already calculated y minus the average of y. So we can give ourselves a little space over here. We could do the square for x minus average. Now you don't need to put anything in here at all if you're familiar with this and are tracking what you're doing. I wouldn't even worry about it. I'm putting these in here at this point just so you can see what the calculation in the column is. So I know that I need to figure out x minus the average of x squared, and I also need to figure out y minus the average of y squared. So I'm just going to title these square of y minus the average of y, just so I know what these columns are. All right. So I have x minus the average of x is right there, and right there, and right there, and right there. I just need to find the square of each of these values. So let's do that. This is going to equal this cell. There's a couple ways you can do it. I'll show you. You can do this cell, and then you hit times this cell again. That's one way to go about it. If you could use the square function, but even easier than either of those, let me just put it in this cell so you can see them side by side. I'm going to use equals this cell, and if you look at Shift 6 on your keyboard, you can see that I can write the formula of E2 raised to the power of 2, which means squared, just like that. And I tend to prefer that maneuver. So I like to do the cell raised to the power of whatever thing I'm doing in this case, and most often you square it. So there it is. Now, when I come in here and Control C, Control V, you can see that it's going to do E2, E3, E4, E5, E6. I have squared this column in each of these cells. Let's do the same for Y, since we also have to solve the Y portion in the denominator. So equals y minus the average of y raised to the power of 2. Very good. Control C, Control V, or drag it down, again, whichever you would like. Okay, let's just bring this over a little bit. All I did was shift over or move over the cells because we don't need the first two columns there really. So now we have solved this top part. So next we need to sum those values that we just got. Well, we've done this before, And it turns out we just have to select that column and sum it, and select this column and sum it. And there we go. All right, now the last portion of our equation, or not the last, almost the last, the penultimate portion of our equation, which means second to last, folks. Let's use that word correctly here. If you hear penultimate, it doesn't mean uber. It means second to last. That's all. That's all it means. All right, side rant over. Let's multiply these values by those values. So here we have squared x minus the average of x and summed it. And here we have y minus the average of y squared and then summed. Now we need to multiply these two together. How am I going to remember this? Let's just put it here. Equals that value times that value, just like that. And let's just call it the product. Again, we don't have to label it, but maybe it helps us find where we're at in the process. So we have the product right there. We need to square root it as the last step. So we've solved that portion, multiplied this values by that value, and now we need to square root the entire thing. So let's do that. Square root that cell, close it off. Sounds good. Let's label it square root of the product. Great. Okay, we have solved for the numerator and we have solved for the denominator. To figure out r, we take the numerator divided by the denominator. So we take the numerator divided by the denominator, and we end up with 0.68 on and on and on and on. Let's bring that in just a little bit. Yeah, why not down to 2? We'll bring it down to 2 decimal places. Let's make it 3. Why not? So our correlation coefficient is 0.968. So keeping in mind that correlation coefficients exist between 1 and -1, with 0 being uncorrelated or no covariance, and 1 being perfectly defined covariance, we are pretty close to 1 with our correlation coefficient. So great. That is a strong positive correlation between our basketball's circumference and our basketball's weight. Wonderful. Let's take a look at bowling balls. So maybe we'll just work through this one really quickly. And we can do it this way. Equals Pearson's, or Pearson in this case. It wants array 1, because of course Excel has already thought you're going to want to do something like this. It included a function for you. Oh, it wants to give me the help thing. I don't want it. So we're gonna make our x-axis the diameter in inches, comma, space, and now we're gonna give it the y-axis as that. Close off the equation, and this will calculate correlation coefficient right there. Should we see see how close we are? We'll call it the Pearson function. So here we'll just use equals Pearson. Yep. Does that again. It's all right. We want our x variable, comma, space, by our y variable. Close it off. Well, look at that. Looks pretty good. Down to 3 spaces. Looks like we did a fairly decent job of that. So using Excel, you can hand calculate each of the steps in what looks like a complicated equation, but really take it step by step. Do this if you need to. Take notes. Write this down. It's what I do because I don't do this every day. I only do it a couple times a year. But when I do it, I want to make sure I get it right. So I will often do exactly the thing that you just saw on here, which is to say I have my data. So I will work through calculating the R sort of by hand, if you will, using Excel. And then I will also use the calculations embedded in Excel itself. So that can be Pearson's R, that can be Spearman's ranking correlation. It can be whatever it is I'm doing. There's a way to calculate it through yourself, and then you can calculate it through with the built-in function. And if the two come out the same, you've done some good work. With bowling balls, we just went with Pearson's correlation or with the Pearson function in Excel, because now that we're familiar with it, we can rely on it. So we take a look at bowling ball diameter as related to bowling ball weight. What does this tell us? Well, it tells us that there is a slight negative correlation. So as X increases, Y tends to decrease, but a figure of 0.45, or let's just bring it down, 0.45 is not a strong correlation at all. So when we take a look at X and the value of X, it is not a strong predictor of the weight that we're going to see. And that's in strong opposition to the way basketballs are correlated. So with basketballs, an increase in size or an increase along the x-axis, in this case circumference, is a very good indicator that there's going to be an increase in y of some type in the strength of that. But how much? That can be a little bit of a confusing question. So that's why we use the coefficient of determination. So let's take a look at this for just a second here. I'm going to bring this back in. We've looked at our data, and we've got a R value by running through this calculation. Wonderful. That's very useful. It gives us a direction of the covariance, and it gives us an indicator of how much error exists inside of that. But it can be a little rough to try to figure out what the actual strength of those things, or how much of a difference matters. The coefficient of determination is often just understood as R squared. And the calculation on it is taking your R value and squaring it. So no complicated calculations on this one. We're not gonna spend too much time on the equation for it. Figure out your R and then square it, and you're gonna have your R squared. But it's very useful because it turns that relationship, let's say between two R values, into a percentage that can be more readily understood by the person looking at it. So the way that you say it is like an R squared of 0.91 accounts for 91% of the error that can be found amongst those variables. Perhaps this helps a little bit. So how much better is 0.07, an R of 0.07, than an R of 0.5? They look pretty close. You know, 0.5 is halfway between 1 and 0. So that's not bad. That's half good, or half correlated. But 0.7 is almost half again between 0.5 and 1. So is that, how much more gooder is that? They seem awful close. As you're asking these types of questions, you figure out your R squared to better understand how much better those two things are. So the R squared of 0.7 is 0.49, or 49%, basically 50% of the variance is accounted for. Meanwhile, the R squared of 0.5 is 0.25, or just 25%. So an R value of 0.7 is nearly twice as good a predictor. It accounts for nearly twice the amount of error represented in your data set. So it's quite strong, one compared to the other. And that is what the R squared portion is used for. So keep in mind, all of these things, you figure out R, you understand the covariance, in which direction they're headed, and R will tell you sort of the strength of that relationship, with the 0 being unrelated, 1 and -1 being very, very strongly related, but also having a directionality to them. And the R squared telling you how much error is accounted for by your R value, and it's especially good at comparing R's across two different data sets, which we could probably do really quickly here. Let's just take a look since we have time. Let's figure out the R squared of these things. So that equals, let's use this one, this value raised to the power of 2. Our R squared is these many digits, which seems like a lot of digits. Let's bring it down. How about 3? So 0.93 is our R squared on the basketballs. What about R squared for the bowling balls? Well, we want to take our result, raised to the power of 2, and we can see that it is exceedingly low. So the difference in strength of these two figures is quite a lot. One is 93%, and the other is 0.2% in terms of how well correlated they are. So it's an incredibly big difference between when we're talking about how well X predicts Y, when we're talking about the difference between bowling balls and basketballs. And that's what these figures will tell you. But we must always keep in mind, while correlation and the correlation coefficient can tell you a lot about describing your data, it tells you nothing about why. It does not imply the causation. You have to use these descriptors to infer or build an argument surrounding what it is you're trying to say. And that's the correct sort of approach or mindset you want to take when you're working with any of these things. Okay. Work through some of that with your data sets. Try to have some fun. It's not a not a difficult task. Just take your time with it. The benefits of learning Excel, even just a little bit of Excel like we're doing here, will pay dividends on down the road for years, guaranteed. So it's well worth doing. Anyway, always let me know if you have any questions. I'd be glad to help out, and we will catch you next time.